Hello, one. So we have another AMC 10-12 problem. So this was a number 20 on the 10 and then number 15 on 12. So what we are told, we have 11 segments like this, right? And then these are all equal to each other and 2 units for each one of these. The area of the pentagon is what we are looking for. So pentagon is not regular, so which is something we love to have, but it's not the case now. So what we know is that all the sides are equal. So that's why we have to kind of use that somehow. So if I look at like one of the triangles, like let's say this is AB, and then let's say this side and this side. This is a triangle with 3 sides are equal, which means this is a equilateral triangle. And same reasoning we do have right here. That's also equilateral triangle. So meaning that this is 60 degrees and this is 60 degrees, which means angle B is 120. And same reasoning on the right side, angle E is also 120. So for that reason, we kind of need to use these. So I'm gonna go ahead and write this just to see for now. And then angle E is also 120 degrees. But other than that, it's not really obvious what to do. But what we can do, since we are looking for the area of the pentagon, it doesn't really matter how you find it, as long as you know one way to find it. So we are good to go with that. So what I'm going to try, I'm going to connect A and C as well as A and D. So if I do this, I will have 3 triangles and I will find the area of those. So ABC, AED, and ACD. So if I combine them all, so then we will be done basically. So to do so, we know the angle B was 120 degrees, and we know these AB and BC are equal, which will force this is 30 degrees and this is 30 degrees. And I didn't know that these are already 60s, which means the segment has to be perpendicular to that blue line. It doesn't have to be exact same as the like another segment that we had as 2 units. So it's really close, but it is not the same line. So we know that this is 2, and then we can use the 30, 60, 90 triangle to make this is like 1, and then this is √3, and this is √3 as well. So if I want to find the area of this ABC, right? So let's go ahead and do that. So the ABC and then ACD. So we can multiply area of ABC because that's the same as AED. So I will just find one of these and then multiply by 2. So let's do that way. And then that's 2 times. We know the AC is 2√3 and the height is 1 unit. So that should be 1 times 2√3 over 2. And plus the ACD is not really immediate. So we just need to find the altitude. So if I draw the altitude somehow, so that might be somewhere right there. So this is going to be 1 unit. This is 1 unit. And we know that AD was 2√3. And if I use the Pythagorean in this right triangle, so I'll call this is H. AH has to be √11, right? Because √12, I mean, 2√3 squared is 12, and then HD is 1, so subtract, that's going to be 11. So that is the AH, which is the height. So then area of the ACD has to be 1/2 times height, which is √11 times base over 2. And if I combine these, simplify these actually, then I will get the answer. So that should be 2√3 plus √11. But we are given both m and n as a number integer inside of the radical. So which is 12 can be, 2√3 can be written as √12, and that's 11. So if you add these two, m and n, so we should have 23. So that wasn't too challenging problem, but it was not really obvious how to kind of get this immediately. So sometimes it's better to look at the figure and see if there is a nicer way to find the areas, because sometimes you given drawing make it harder. So if that's the case, sometimes like try finding some other approaches, and then this is, I guess, easier. As a side note, like I never use this in this problem, but it's good to know. If you do have a 120 and 30 degrees triangle. So let's say this is same as this one, and this is 120. This is 30 degrees, and this is 30 degrees. And if this is x, this is x, and then this side should be x root 3. This is one of the other special triangles that actually help a lot. So that's why I will say go ahead and try like dropping some altitudes or extending segments to prove this on your own by using 36 and 90 degrees triangle. So that might be useful in a lot of different cases as well. So I'll see you in the next video.